Displacement wave. What does a displacement wave actually stand for? When we are talking about a displacement wave, a particle, when it is moved from one point to the other, for instance, if you were talking about the ripples, if you just drop a stone, then if the stone also moves with the ripples, that produces what is known as a displacement wave, because the particle itself is getting moved, or it may so happen that the energy is transferred. This happens in the case of displacement wave. Let's learn more on this. So students, the next topic that we are going to discuss now is the displacement wave. So what basically does displacement wave stand for? As we have been discussing, when any particle is dropped, let's say in a still water, any stone or anything that is dropped in a still water, it creates ripples. And what is the result of that? Those ripples create waves. The waves move in the forward direction. Those kinds of waves that are resulting as a result of that is what is known as a displacement wave. So when we are talking about a displacement wave, as you can see, these are the ones which represent displacement waves. So what exactly is a displacement wave? Let me explain. A longitudinal wave in a fluid, that is liquid or gas, mind you, we are not talking about solids, can be described either in terms of the longitudinal displacement suffered by the particles or in terms of the excess pressure. Because when the particles are moving from one point to the other, obviously there is going to be some amount of pressure that has to be exerted. As a result of pressure, there is going to be a difference in pressure. Some regions there is going to be high pressure, some other regions there is going to be low pressure, right? So as a result, because of this difference in pressure, there is what is known as the production of a displacement wave. Now let's try to understand the mathematical formula for that. Let's say the displacement S is in the x direction. It is given by S is equals to S naught sine omega t minus x by v. And how do we get it? If you remember, we had written down an expression like y equals to y naught, something like sine omega t minus kx. Yeah. So if we write this down, so if we take out the factor of omega out, so what will we get? We'll get sine, here we'll get omega, here we'll get t minus k by omega into x. But k by omega, that can be simplified, and you can write this as omega y naught sine omega, and here you get t minus, this can be written as t divided by lambda into x. So t divided by lambda is nothing but the wave velocity. So we can write down in terms of the wave velocity, and we get t minus x divided by v. That's the result. You get something like this. So now here what you have is this, that if you say that you have an atmospheric pressure that is being acting, apart from that, how much is the pressure that you're applying at this point? If you take a small tube, so obviously on both the ends the same amount of atmospheric pressure is going to be acting because they are at the same height. Yeah. So since they are at the same height, so there is going to be an atmospheric pressure, and in addition to that there is going to be an applied pressure. The applied pressure on the left hand side is going to be different from the applied pressure that is there on the right hand side. So if we take that into account, so obviously if there is any wave that is going from one point to the other, they may be at different heights, let's assume. So we have x1 and y1, x1 corresponding to the x coordinate, y1 corresponding to the y coordinate. Now, since there is both a difference in the x coordinate and the y coordinate, so that implies that the area of cross section on both the sides are going to be different. So if I say A into delta x, that's going to be the amount of volume or the change in volume for a constant density of whatever it is, whatever is the thing that is flowing through it. So if we take the density to be rho, so rho times A delta x gives the amount of mass that is being moving from one end to the other. This difference in the mass that is moving from one end to the other creates the displacement waves. So as the wave passes, the ends at x and x plus delta x are displaced, let's say, by the amount s and s plus delta s, and s is given by this particular expression. So this is what is known as the formation of the displacement wave. Going further, if we try to explain it further, so what will we get? Let me change the color of the pen. So we have the increase in volume, as we saw that A delta x is the change in the volume. So obviously it's going to be an increase in volume as time passes. So it's going to be equals to A into delta S. And how will you represent it? So A into delta S can be represented as the partial derivative of S with respect to x. There can be other factors which may be changing, but we are not concerned about that. Yeah. So we'll just be concerned about how much is the change in the displacement that is taking place. So A into delta S by delta x. So as a result, we can say that the change in volume is equals to A. I'm just coming from here itself and using the same formula. Let me rewrite that same formula here. That is S is equals to S naught into, you have sine, further you have omega, then you have T minus x divided by V. So if you differentiate this with respect to x, mind you, so there is a factor x here. So if you differentiate omega by V is going to come out. So A S naught minus omega by V comes out. Then you have cos. Okay, there is this factor of omega that is missing from here. So that is the one that is produced. Now, when anything is moving, obviously that creates a pressure difference. But let's try to take it subjectively. If there is a pressure difference that is created, that pressure difference is going to be everywhere. And when we are talking about any fluid, we say that it is related to the bulk modulus, because for the case of bulk modulus, it is related to the change in volume over the original volume. Because if you want to find out how much is the volume, original volume affecting the change in volume, so using that into account, we can say that P, that is the pressure, is equals to the bulk modulus into the change in volume upon the original volume. So as a result, we can say that the pressure also has, let's say, pressure amplitude P naught and the displacement amplitude S naught. So we can relate that. As you saw here, S naught was nothing but the displacement amplitude, A was the area. So using these facts into account, we can find out how much is going to be the pressure. So pressure, okay, make you understand. You have delta V. So if I just divide by the factor of V, so what will I get as a result? So I can simply say that P divided by B is equals to minus delta V divided by V. Yeah. Now here what you have. So if you try to find it out from here, so if I just take the magnitude part, I'm not concerned about the negative sign. So what will I get? I'll get A S naught, or even if I take into account the magnitude or even the sign, it will not, is finally not going to affect, because there is a negative sign here, there is a negative sign here, so effectively it becomes positive. So effectively you get A S naught divided by V, then you have omega divided by the velocity, cos, you have T minus x by V into delta x. So this is what you get, right? So if we combine all of that, if we combine all of these things into account, so that is going to give you something like this, because A into delta x is going to go off with the volume, S naught is going to stay, omega is going to stay, V is going to stay. Rest of the things are going to remain as it is. There was a factor of omega that was missing, so that is going to come out here. I have corrected that and it comes out here. Hopefully this makes sense. So this is how the pressure is related. Now if I just try to combine, so you can see that this particular factor gives me the pressure amplitude. So the pressure amplitude is given by B omega divided by V to S naught. And if I just come omega by V, and because if you see the last slide, I just showed it to you that what is V. So I can get back in terms of the wave number K, and it comes out to be BK S naught. So this was the case of the displacement wave. Your K is nothing but the wave number. Let's move forward and try to talk about in the case of pressure waves. So what basically is a pressure wave? So when a pressure wave reaches the ear, so obviously you will see a series of highs and lows. Pressure, some regions where the pressure is going to be high, which are going to be represented as the red colors, and the blue represent the ones where the pressure is low. So the arrival of a compression of or high pressure region pushes the eardrum inwards. Because of the push, it goes inwards and then it bounces back. That is because of the low pressure region. So this continuous to and fro motion, arrival and departure, results into the eardrum into a vibration motion. That tells us about the different types of sound that comes into our ears. Now let's try to identify it. Let's try to understand it further. So the fact that displacement is 0 where the pressure change is maximum and vice versa puts the two descriptions on two different footings. Let's try to understand what do we mean by that. The pressure wave equation, if you try to understand the pressure wave equation, it is nothing but similar to the wave equation that we have in quantum mechanics as well as in normal wave equation. So this basically, as you can see, there are two variations. This is the partial derivative with respect to x, how it varies with x, and this is the partial derivative with respect to time. How do we get it? Let me give you a very simplistic way to understand it. You know that the pressure equation can be simply given by P equals to P naught, and then you have sine, and here you get omega t minus k into x, right? You differentiate this expression twice with respect to x, and similarly you differentiate this expression twice with respect to the time t. You will have in terms of omega by k. Omega by k in the case of pressure waves is going to be represented, omega by k is going to be given by c. So that c is nothing but the velocity of the pressure wave, which is nothing but the speed of light. So if you just need to do a couple of steps, that's going to clear everything up. So let me try telling you how to do it. So let's say if you differentiate this with respect to the time t, what will you get? You'll get P naught omega cos omega t minus kx. Then if you differentiate it twice, that is d square p over dt square. So this comes out to be equals to minus P naught omega square sine omega t minus kx, right? This we got it. Now let's differentiate it with respect to x. So if we differentiate it with respect to x, we are going to get similar kind of thing. So we'll get d square p upon dx square. So that's going to come out to be with a negative sign. We'll have minus P naught k square sine of omega t minus kx. We take a ratio of omega by k, that's going to be equals to c square, means taking it accordingly will give you c square, and c square is nothing but the velocity of light square, because this is related to the case of electromagnetic wave motion. Let's move forward. What exactly, with taking these things into account, we can understand about how the sound waves move in solid. The speed of sound in solid, or in a particular solid rod, solid material, uniform solid rod, is going to be given by this particular expression. What basically this represents? Here, rho represents the density and gamma is related to the bulk modulus of the solid. So this is how the sound is going to be related, or the velocity of the sound is found. Now, if we try to combine or try to compare, we'll say that in a dry air, the speed is like this. In copper, the speed of sound increases like this. So as the density increases, you can see that the velocity of the sound is also increasing. So therefore, the sound moves like this. So this broadly tells us about what all it depends upon. Taking these things into account, now if we try to understand about the intensity of sound waves. So what exactly or how exactly do we are going to find out? The intensity as we have seen before, it is related to the amplitude, how much is the displacement that is taking place over a particular amount of area. So it's the average energy crossing units cross-sectional area perpendicular to the direction of propagation. So if we are saying that this is a kind of wave that is moving, so from here you can see that obviously this represents the crest and trough. But if you have to look into it, how much is the amount of energy that is passing perpendicular to that area, that tells us about the intensity of sound. So we can also state this as the average power that is transmitted across a unit cross-sectional area, obviously perpendicular to the direction of propagation. That is what is known as the intensity of sound waves. So higher, as you can see, a smaller peak or smaller distance between the peaks is going to produce a lower sound, and a wider one is going to produce a higher amplitude of the sound. Amplitude square is nothing but it is related to the intensity. So that is how we relate it. Now if we have to find out I being the intensity, so the amount of intensity, the intensity I is proportional or is equal to the average power that is transmitted across unit cross-sectional area. So I is going to be equal to half omega square S naught square. S naught is basically the amplitude of the displacement, B is the bulk modulus, V is the velocity. So if I combine all of this, so this is what we are going to get. Here B is nothing but rho into velocity square. The intensity, we can also write it by this particular formula. So as we see, the intensity is proportional to the square of the pressure amplitude. So as I just mentioned, higher is going to be the amplitude, higher is going to be the intensity, because square of the amplitude gives you the intensity. So this is how the intensity of waves are related to each other. Now if we move on and try to understand about the relation of intensity and pressure. So what exactly is going to be the relation of intensity and pressure? So there are a couple of relations that we should understand. So P, that is the pressure P, is proportional to it's inversely proportional to the distance at which we are trying to find out. So that is P is inversely proportional to R. Then the intensity I is going to be proportional to P square. That is, the more is the amplitude, more is going to be the intensity. Intensity is going to be very inversely as R square. As you try to measure the intensity at a longer or distant point, the intensity is going to decrease. Pressure is going to be directly proportional to the square root of the intensity, because pressure is nothing but the amplitude. So that should be proportional to the square root of the intensity. Now if we try to compare the two pressures, so that's going to be dependent upon the distance at which we are trying to find out. Longer is the distance, less is going to be the pressure, and vice versa. Therefore, from here you can derive these couple of relations. I2 by I1, because it's going to be inversely proportional to the distance square, effectively gives you a relation for the pressures. Similarly, with distance and intensity, you can find out a relation. As we discussed in the case of displacement waves, that if you have particles which can move from one another, we say that there are waves that will be associated with that, and those waves will be related to the transfer of energy from one point to the other. So these type of transfer of waves which are produced are also known as the displacement waves. Now, have you ever wondered that supposing you have a loudspeaker that is sounding in front of your eyes, or let's say in front of your ears, you hear a very loud sound, and sometimes that loudspeaker, let's say, it may be very far away. In that case, the same sound becomes fainter. So what is the difference? Let's now try to understand about that in our next part.